Hi, this is Professor Stugard, and in this video, we're going to be discussing the basics of functions of two variables. But before we get there, let's start off with an example from our previous videos, and this is a problem we've done a couple times. Find the equation of a plane, and this time we have our normal and we have our point, and so if I keep reiterating this over and over again, man, finding the equation of planes and understanding plane surfaces must be a pretty important part of this class, huh? Well, the best part is, though, again, like I said, we've done this before. We know the formula. All we have to do is take our formula for the plane and plug in all of our numbers in the correct spot, and then just simplify properly. So, again, we plug in our normal vector for the a, b, and c. We plug in our point for the x0, y0, z0. And then it's just a matter of simplifying. So distribute. And then once we distribute, we're just going to combine like terms, which in this case are just my constants. Now, there are two ways we can do this. Obviously, we have minus 2, minus 12, minus 30, which is minus 44. And you can leave the minus 44 on the left side. I like to put the 44 back to the other side. It just looks more aesthetically pleasing to me. There's no right or wrong way to do it necessarily. That just looks slightly better to me. But again, given the normal, given the point, we can find the equation of the plane. Hopefully this is all easy review. But if I can take that equation, I'm going to be able to solve that for the variable z, meaning I can isolate z on that left-hand side. So the first step, let's subtract the terms with the x's and the y's. So you have minus 2x and minus 4y now on the right-hand side. And then lastly, just divide everything by 6. And after simplifying our fractions, I'm going to get negative 1/3 x minus 2/3 y plus 22/3. And what I've done here is I've now isolated z on the left, and everything with an x or a y, or a constant, is now on my right-hand side. And this is how we're going to define our functions of two variables. If I can isolate z on the left-hand side and move everything else to the right, everything on the right is going to consist of x's and y's and constants, and it's still going to describe some surface in 3 space. We still have our 3 variables. It's just, if I can get z by itself, it's going to make life way easier. And that's because the way we're going to think about this is kind of a little bit, well, in reverse of how it's typically written. If I have the x's and y's on my left-hand side, that's some function with x's and y's. That means I'm going to be able to plug in an ordered pair xy, and it's going to output a single value for z. And the way we think about this, if you remember back to our very first video, is that z is really our height. And so I'm going to plug in an ordered pair in my xy plane, and it's going to output a single value z, which I want to think about as my height. Mathematically, what we're doing is a mapping. And so a mapping is basically where we plug one thing in and get another. But in this case, with our functions of two variables, what we're doing is we're mapping an ordered pair in R2, and it's going to map to just a single value in, well, the real numbers, or on the real number line. And this is going to be the most useful way we have to describe what's going on in R3, or in 3 space, right? We have an ordered pair, 2, that maps to 1. 2 plus 1 is 3. It describes 3 space. And it's the same idea that, that we can kind of expand upon in further math classes. So again, in multivariable calc, in Calc 3, we typically stick to, well, 3 space for the most part. Towards the end of the semester, maybe we'll get into some 4-dimensional stuff. But typically we stay in 3 dimensions because I can still graph it. I can still visualize it. I can still see it. It's not necessarily easy to see on flat sheets of paper or even on a computer screen, but we can make use of our projective drawings and get an okay idea of what's going on. But when we expand to even higher dimensions, it gets a little bit trickier. But luckily, all of the mathematics is still going to hold, and all the mathematics is still going to be true, even if we can't necessarily visualize it very well. And that's actually what complex analysis is. If you're a math major and you're going to continue on, complex analysis is really taking, well, complex numbers, which remember actually have two parts, right? A complex number has a real part and an imaginary part, so it's actually a two-dimensional number. And if I plug a complex number into a function, it's going to output another complex number, which is in 2 dimensions. So I'm mapping 2 to 2. And so complex analysis is really just the study of how we describe 4-dimensional space. And again, we can expand this into as many dimensions as we want. And if you're a computer scientist, or you're a data scientist, or someone who uses linear algebra, you can expand this to as many dimensions as you want. Everything we do in this class is going to be applicable to even more complicated ideas. But sticking in R3 and sticking with our surfaces in 3 dimensions, even if I can use computer software to graph them, it's not always particularly useful because it can still look kind of cluttered. So one of the ways that we try to help understand what's going on with a 3-dimensional surface on our 2-dimensional paper is to use level curves. Now you might even have seen level curves before, because we use level curves typically to represent points that all have the same height. So if you've ever studied a topographical map, or we even do it with the weather, where we have temperatures instead of heights, basically we take a 2-dimensional picture and overlay different curves that all represent the same value. So let's just do a brief example. So consider this topographical map. All right, and so you can see that this topographical map has a bunch of lines, and they all denote different heights. So you have, 5 feet, 10 feet, 15 feet, 20 feet, 25 feet, and so on. And again, they're all connected. Every point that lies on those lines has the same exact height. And so the way we can use level curves is, well, let's just start with problem A. Let's approximate the height at the ordered pair 2, 4. In other words, if this was some function of 2 variables, I want to evaluate f of 2, 4. Well, that means my x-coordinate is 2, my y-coordinate is 4, and we see where they intersect. And where they intersect, that intersection point is going to correspond to some height. Now, in this case, it looks like that's pretty close to 30. Now, we're just doing approximations here, so it doesn't have to be exact. It's probably a little bit more than 30 based on the picture. But again, we're just approximating. And so approximately at the ordered pair 2, 4, we're looking at, well, roughly a height of 30 feet. Part B, well, where's the highest elevation based on this topographical map? Or in other words, what's the maximum of my function of 2 variables? Well, we can scan this map fairly quickly, and hopefully we can see that the biggest number, the highest height, is over here at 55 feet. And so, well, what does that correspond to? What ordered pair does that correspond to? And then it's just, well, again, the same idea. What's my x-coordinate? What's my y-coordinate? Now, again, it's not perfect and it's not exact. We're just trying to approximate here. So I'm going to say that happens at approximately the ordered pair 5, 5. Or I'm going to have my maximum height at approximately 5, 5. Part C, where are these level curves the closest together? And then what does that actually mean? So when I take a look at this picture, it looks like right there. It looks like that's where my level curves are going to be the closest together. So what does that mean? Well, inside that circle, we went from a height of 0 feet all the way up to a height of 45 feet in a very small space. In a very small circle, I was able to go from 0 feet to 45 feet. So, well, that means that, again, think about standing at the base of a mountain, right? If the mountain goes from 0 feet to 45 feet in a very short period of time, well, the height is changing the fastest there. This is the steepest area on the map, which means this is the maximum rate of change for the height. And now we're finally getting into some calculus here. Everything up to this point has mostly been just, well, trying to get the basics down of functions and vectors and stuff like that. Now we're starting to actually investigate some of these calculus things. And level curves are great for actually investigating that calculus concept of maximum rates of change. Clearly, my heights are changing very, very quickly in that small period, in that small little area. And that means that it's the steepest, which is my maximum rate of change. And when we start measuring rates of change, we're probably talking about derivatives, aren't we? And we are, and we'll get there. And level curves will come up again when we start talking about other concepts later on in the chapter, like the gradient and those sorts of things. And part D, same question but reversed. So where are the level curves the furthest apart? Probably that big open area there. And I even drew a much bigger circle. And we see even in that bigger circle, the height only changes about 15 feet as opposed to 45 feet in my small circle, which means this is definitely the flattest area on the map. The height is changing the least. Now, obviously on a map, every point's going to be defined, but that's not always the case. Obviously, our functions of two variables are going to have domains just as our functions of one variable had domains. Now, for a function of two variables, the domain is going to be ordered pairs x, y. And again, it's the ordered pairs x, y that I can plug in and get a value, which means that if I'm plugging in x, y and getting a value directly above it, well, that means that the surface must be directly above its domain in the xy plane. Or it could technically be below, but it's going to be right in my xy plane. And that means the projection on the surface of my xy plane is actually going to be the domain of my function. Which also means that, again, many times it's going to be very useful to sketch the domain in the xy plane to get a better idea of what's going on. So let's say I'm given this function of two variables, so f of x and y, that equals the square root of the quantity 2x minus y. What's the domain? Well, luckily, all of our rules for domain from single variable functions still apply. This is a square root function. And we know that for a square root to return a real value, the radicand, or the part underneath my radical, has got to be greater than or equal to 0. It must be non-negative. My radicand is non-negative. Well, my underneath part is 2x minus y is greater than or equal to 0, and that's actually a perfectly acceptable way to describe the domain of this function. That's an absolutely true statement. It's not always necessarily the most useful because, again, if we're talking about something in the xy plane, typically isolating y is going to be the more useful way to, understand what's going on. And then, of course, we can graph it. And so if y is less than or equal to 2x, well, there's my domain. And every ordered pair in the blue is going to be part of my domain. So, for example, the ordered pair 3, 0 is absolutely going to be in my domain. Sure, plug it into this function. We can absolutely get an answer. Whereas the ordered pair negative 1, 2 is not in my domain. And again, we could check that very easily by just plugging it in and seeing, well, no, we're not going to get a real value. And so now I understand where this function is actually going to exist in my xy plane, which is where it's going to actually exist in 3 space as well, directly above my xy plane. Next example, find the domain of this function of two variables. So f of x and y equals the natural log of y plus 1 over the quantity x minus 2. And well, the first thing I see is my natural log function. And I know that the domain of my natural log has got to be, well, positive values. I'm only allowed to plug in positive values into my natural log. No zeros, no negatives. Well, that means that my expression is that inside that natural log, y plus 1 has got to be greater than 0. And we're good there. Or you could, of course, solve for y has got to be greater than negative 1. And then, well, I also have a rational function. And I know that the denominator cannot be 0. So x minus 2 cannot be 0, or this is a very easy one to solve. So, and we have the fact that x cannot be 2. And again, we can graph that ourselves. We see that y has got to be strictly greater than negative 1, which is this one. Just pay attention as well that when we do this one and it is a strict inequality, notice how it is a dashed boundary line. We use a dashed boundary line for our strict inequalities because I cannot include those values. I cannot include anything on the line y equals 1. And then we also have x cannot be equal to 2, which is denoted by that line there. So let's go back to level curves again. So a more formal definition of level curves. Level curves are the two-dimensional curves for a function of two variables, where we set z equal to some constant, where k is your constant and k is any real number. Now again, you can't choose any real number you want, although typically integers tend to make the most sense because they're just easier to work with. But the main idea is that these level curves are going to be the same exact process as finding our traces. Remember, traces are just our intersections in planes, so our level curves are really just intersections in planes. The only difference is that we're going to graph several level curves together, and if we have more level curves together, we're going to get a better understanding of the surface in question. So let's investigate this surface. The function f of x and y equals 4x squared minus y squared. Well, let's start with z equals 0. My first level curve is going to be z equals 0. And so if I plug in a 0, 0 equals, well, 4x squared minus y squared. It equals my function. And this is a perfectly valid way to find our level curves, and especially if you're using technology. Technology can graph this level curve for you, well, almost instantly. But sometimes, again, it is more intuitive to solve for y. So I could add that y squared to both sides, take the square root of y, and then just be really, really careful. If you're taking a square root, we need that plus minus symbol. Don't forget to include that plus minus symbol. And then, of course, we can graph it. And so my first level curve is going to be y equals plus or minus 2x. So there's my first level curve. So at z equals 0, my function is going to intersect the plane z equals 0, or my coordinate plane, just like this. Then my next one, z equals 1. So again, just plug in a 1. 1 equals 4x squared minus y squared. And again, I'm using Desmos.com to graph these, and it can graph that equation perfectly and instantly. If you'd rather solve for y, you can obviously solve for y, and y is going to be plus or minus the square root of 4x squared minus 1. And then we get my second set of level curves, and then let's plug in 2. Z equals 2. So 2 equals 4x squared minus y squared. And again, if you want to solve for y, of course you can. And we start looking at these level curves, and I'm looking at, oh, well, these are graphs of hyperbolas. These are hyperbola graphs. My curve, my function must be some sort of hyperboloid in space. And we can graph even more, and we can still apply those same things from looking at my level curves, where's the maximum rate of change going to occur? Well, the maximum rate of change is where my level curves are really close together. So I'm going to have a maximum rate of change towards the, well, I guess those almost the four corners of what I drew. All right, these are where the level curves are closest together. That means that's the maximum rate of change. It's going to be very steep there, whereas towards here around the origin, they're further spaced, which means it's going to be not as steep. It's going to be less steep there. Now, go ahead, use Desmos. Plug in a few more values. Plug in 3, 4, 5. Get a better idea of what's going on and actually take a look. Play around with these things. Use GeoGebra. Use Desmos. Use technology on your own time to try to get a better understanding of what's going on. The better intuition you have for this stuff and what's going on and in recognizing what kind of functions look like what is going to help you later on when we start doing things like integration in Chapter 15, where you're just going to be given just equations and asked to, well, do math on them. And if you develop your intuition now, it will absolutely help you quite a bit later on. All right, well, that's the main stuff I wanted to talk about with functions of two variables, at least getting started. So take your time, work on the homework, and as always, please email me if you have any questions. Good luck.